All right, so we are going to discuss questions from moving coil meter. This is the question. First question is from 1992, but there is a small problem with this question. Data is missing. Okay, data is missing. I think Zainab Hussain asked me a doubt about this question. In this question, they have mentioned, right? This is the circuit they have given: a voltmeter, a voltmeter of internal resistance RV and a meter of internal resistance RA are connected to measure a resistance R as shown in the figure. This R as shown in the figure. Okay. R shown in the figure. Then R dash is there in the question. It's not explained to us properly. R dash is actually this. R dash is equal to the ratio between voltmeter reading and ammeter reading. That is R dash. Voltmeter reading and ammeter reading. Okay. But if possible, I'll try to share the Tamil medium version of this original question. Wait. I think it will be beneficial for us if we can share it. Tamil medium version of it. Wait a minute, where is that? Yeah, this is 1992 question number 15. Okay, 1992 question number 15. In that they have told வோல்ட்மானி வாசிப்பு வீட்கும் அம்பெமானி பதிவு செய்யும் மின்னோட்டம் ஐக்கும் இடையே உள்ள விகிதம் தருகின்ற தடை r டேஷிற்கும் rக்கும் இடையிலான தொடர்பு. Right, they are saying r dash is the ratio between the voltmeter reading and the ammeter reading. Okay, and then they are asking for the relationship between r dash and r dash and r. So this is r dash. In the answers you have you have r dash. People see here you have r dash, r dash, r dash, r dash. Yeah. Okay. So what is that going to be? And wait, the ammeter has an internal resistance of RA. Voltmeter has an internal resistance of RV. Okay. So we have to focus on this now. How do you do it? These two are going to be parallel, aren't they? These two are going to be parallel, but this R naught is there. R naught is there. R dash. Okay, whatever the voltage we have across this one, we'll have the same voltage across this one as well, no? And they haven't told that this is an ideal voltmeter, so there's a current flowing like this. I, same current will be flowing like this, I, through the battery as well. But that I is going to get separated here, no? I is going to get separated here, and that is going to be like, I don't know, IV. That's the current through the voltmeter, and IR current through the resistor R. So what are the things we can figure out? These two should have same. Voltage. These two should have same voltage, and R naught is not there in the answer, no? So I don't think we have to worry about R naught here. R naught is not there in the answer. The meter reading is I. We have to figure out a relationship for I now. Right, so let's try to write equations for V here. Equations for V. V, according to the diagram, it is going to be IRR, no? IRR, and also V is equal to this one, IVRV. IVRV, that is the voltmeter reading. Current is the problem now. When you add IR and IV, you will get the current through the ammeter, that is I. Okay, that's it. So here from these two, wait, I'll do it this. I think this is not going to be very difficult as we thought it is going to be. So you mark all these things. Then first of all, for R, you apply V equals IR. V equals IR. Okay, V equals IR. So V for R, it is just V once again, the V, and I is the current through R, that is IR, and the resistance is R. First equation. And if you apply the same equation for the voltmeter, voltage is equal to IR, voltage across the voltmeter is also taken as V, the current through that is IV into RV, RV is the internal resistance. Second one. And we know current IR plus IV is going to be equal to I, that's the current through the ammeter, total current. So from this IR we can write what we can write IR this way, no? IR is equal to V over R, correct? IR is equal to V over R plus what is IV, people? IV is equal to V over RV equal to I. Understood? I hope you guys have got it now. I think this question is very simple, even though it looks complicated. You can make IR the subject here. IR is equal to V over R, no people? VR. And if you apply the same equation for the voltmeter, V equals IR, then voltage across the voltmeter is V, current IV into RV. No? That means IV is equal to V over RV. Now the question is, voltmeter reading over ammeter reading is R dash. So R dash is in fact equal to what? R dash is going to be equal to what is the voltmeter reading? V. What is the ammeter reading? I, according to the diagram. V over I. So what I have to do is, I have to find a relationship between V over I. Then what I'm going to do is, we know IV plus IR. IV plus IR is equal to total current I. The current going through the voltmeter and the current going through the resistance, both when you add them both, it will be equal to I. What is IV? This one, V over RV. And what is IR? That is V over R. And what is I? We leave it as I. And then either side will divide by voltage. When you divide either side by voltage, the left hand side will be 1 over RV plus 1 over R equal to I over V. Right side will be I over V. Can Salman tell me what is I over V? What is I over V? What is I over V? Anyone? I over V is going to be 1 over R dash. 1 over R dash. Because we just wrote R dash is equal to V over I. That means 1 over R dash has to be I over V. That's all. Correct? E, R naught, they are not our problem. We just have to focus on this area. Therefore, what do you think is the most suitable answer? Looks like the third one is the answer for this question. So Zainab Hussain, please include this in the question. I told you there's a mistake in the question. Data is missing. Okay, everyone, include this part in your question. Huh? The ratio between the voltmeter reading and the ammeter reading is given by R dash. Then what is the relationship between R dash and R? That's the question. Okay, just check the Tamil video one. Please include that. This. If not, you can put it this way. If not, you can write it as a sentence saying that the R dash is equal to the ratio between voltmeter reading and ammeter reading. Done. So that's the first question for you. And then moving on to the second one. This is from 1992. The second one is going to be from 1995. Yeah, interesting. So this also, I think Zainab, you had a doubt in this one, right? A galvanometer that reads 1 milliampere for a full scale deflection. 1 milliampere for a full scale deflection has a resistance of 75 ohm. The galvanometer can be used to measure current up to 1 ampere by connecting a 0.751 ohm resistor in a suitable manner. Right, okay. Now, if you use the galvanometer normally, it can read a maximum current of 1 milliampere, right? But we are going to connect a 75, we are going to connect another resistor in suitable manner so that we are able to measure a 1 ampere current. If you want to measure a 1 ampere current using this 1 milliampere galvanometer, how should the shunt resistor be connected, people? We should connect it in parallel, shouldn't we? We should connect it in parallel like this. So we have to put a shunt resistor. And the value of the shunt resistor is provided to us. The galvanometer can be used to measure currents up to 1 ampere. Okay, 1 ampere current can be measured, but through the galvanometer you can send only 1 milliampere current. That's a different story. So we have to divert the remaining current. That means we have to divert the remaining 999 milliampere current through the shunt resistor, and that shunt resistance is given to us. How much is that? That is how much? 0.751 ohm. In a suitable manner, this is a suitable manner, you have to put it parallel. The value of effective resistance of the ammeter, the value of effective resistance of the ammeter. How do you find the effective resistance of the ammeter, people? When you say effective resistance of the ammeter, indirectly what are they saying? That is the resultant of internal resistance of galvanometer and internal resistance of galvanometer and shunt resistance, correct? Because both of them are connected in shunt resistance, because they are asking effective resistance. So resultant of internal resistance of galvanometer, internal resistance of galvanometer is given by 75 ohm, and shunt resistance is given by 0.751 ohm, and both are connected in parallel. Remember, both are connected in parallel. 0.751. Okay, 0.751. So what is the answer for this question? 0.751. You have two resistors. Okay, you have two resistors in parallel, and 0.751 here. So when you have two resistors in parallel, people, we have learned, now you can find the actual value, but when you find the actual value, I don't think you are getting any of these answers. There's a problem there. Yeah, I think there was a problem with that. Yeah, it is 0.751 resistor, suitable manner. 75. So one thing we can say is, now resistance of I should put equivalent resistance of sorry, it should be equivalent resistance of equivalent resistance of equivalent I have put resultant of, sorry, correctly I have put it correctly, resultant of, right, this. So resultant of, that means this. So resultant should be what? So resultant resistance should be, should be less than should be less than 0.751 ohm and 75 ohm. Why? Reason is because they are connected in parallel. So which answer do you think is the most suitable one out of the answers? There's only one answer which is less than 0.751. This is also less than 0.751, but it's almost the same value. So I think it should be smaller than this. So the answer is, so suitable answer, third one. Suitable answer should be the third one, because it has to be a value less than 0. And I have a problem with this 75 ohm. If you put if you try to find the resultant, what is happening when you have two resistors in parallel? You have two resistors in parallel. One is 75 ohm. This is given as 75 ohm, and this is 0.75, right? So if you want to find the resultant of them, we know 1 over R equals 1 over R1 plus 1 over R2. 1 over R we have to find out. 1 over R1 is 1 over 75 plus 1 over 0.751. We'll write it this way: 1 over 75 plus 1 over 751 by 1000, that is 75 plus 1000 over 751. So roughly if we take it as 750, then it will be 10 over 750 plus 1000 over 750, roughly come go. That means 1 over r is finally equal to yeah, I should put roughly here. You can approximately consider it this way, no? Approximately I can say 10 over 750 plus 1000 over 750. So 1 over r is approximately 750. On top we will be getting 1010, that is 101 over 75. What is the answer we are getting for then r? R is equal to 75 over 101. So we are getting which answer? The answer is less than, oh yeah, 707 in 43 404. We're getting 0.74 as the answer. But there is no answer like that. So I think no, this question has a problem with it. If you do it that way, if you try to find the actual value, this is the answer we are getting, 0.74, by putting the values of galvanometer and the shunt resistance. Might have to check the original paper whether there is a change. Anyone has the original 1995 paper? Check the numbers, will you? Original 1995 paper. Yeah, 1995 paper. What does it say? Are the numbers different or is it the same? Here 24, it's a 24th question. Right, yeah. So even in the review, it's given like that. Even in the review, they have mentioned that way. You don't have to do any calculations. That's what they are saying in the review. They're saying you don't have to do any calculations here. All you have to do is choose the value which is less than 0.75, because they have put two resistors in parallel. Therefore, the final answer has to be a number which is less than 0.75. But mathematically, we are not getting that answer. So looks like with this question, we have to do it with this idea. We do this question with that idea. But Amna, do you have the paper? Did you check it? It's in the 20 odd 22 or 24, something like that. Check whether any of these numbers are different. 75, 0.751. 0.751 is okay, same, but 75, not sure. And anyways, let's not get stuck in this and let's just move on. I think basically that's what they are expecting us to, that's how they are expecting us to analyze this question. When you put two resistors in parallel, the resultant will be the smaller than both the resistors, no? Smaller than both the individual resistors. So 2, 4 and 1 are definitely wrong. 1, 2, 4 definitely wrong. We have to choose between 3 and 5. We have to choose between 3 and 5, and between 3 and 5, 3 looks the small number, no? Right. Yep. Yes, in the original paper also it's the same paper. So let's leave it and move on. I'll go with the third answer. Right. Next question. Is it 0.075? Oh, wait. This one. Hold on. That's it. In the original paper, this is 0.0751, it seems. Now that is the problem, come on. The original paper, this is 0.0751. That's the issue, people. Sorry. 0.0751. So let's correct that. Sure, you're wasting all this time. Then definitely there's only one answer, people. 0.0751 means definitely there's one answer. We don't have to waste our time with all these things. Correct? This is 0.0751. That's a printing error. That's the problem. In this Pesuru, they have made a mistake. 0.0751 ohm. If it is less than 0.0715 ohm, there is only one answer. So the resultant resistance should be less than what? 0.0751. Please correct that also. Correct that in the paper. So we have tried 2 questions. In both there are printing mistakes in the Pesuru book. That's a shame. Okay, fine. Anyways, now it's quite clear, people. Now it's quite clear. Your answer must be less than 0.0751. There's only one answer. That's the third one. End of story. I'm going to move on to the third question. The readings VA, VB, VC of three properly calibrated voltmeters ABC when connected separately across a certain cell are as follows. When all 3 voltmeters are connected across the cell at the same time, their reading will most probably be. Okay, interesting question. Let's see. 1996 readings of the readings VA, VB, VC of 3 properly calibrated voltmeters when connected separately across a certain cell are as follows. Okay. When all 3 voltmeters are connected across the cell at the same time, their readings will most probably be. So they have given a right, they have given an answer like that. Now we have to understand something. There is a battery. That battery is definitely going to have something. What is it, people? Tell you. Battery is definitely going to have something. What is that? The battery will have something. What is it? The battery is going to have an internal resistance. The battery is definitely going to have an internal resistance. Yes, there is definitely a simple R in the battery. There is definitely a simple R in the battery. And then tell me, why is it showing different readings for different voltmeters? Anyone? Now this is voltmeter A, voltmeter B, voltmeter C. It's the same battery, E, R, E, R, E, R, right? It's the same battery. It will have the same EMF, same internal resistance, same R, but the voltage here is VA, the voltage here is VB, the voltage here is VC. What's the reason? Let's see the answer. Resistance of internal resistance of voltmeters are different. Very good. Internal resistance of the voltmeters are different. Internal resistance of the voltmeters are different. So for this question, you should not do any calculations. Okay, you should not do any calculations. I'm just putting this for your understanding. VA, VB, VC, they will all have internal resistance. So this is going to be RA, RB, RC. Okay, RB, RC, and remember there's going to be a current now. There's going to be current coming out of the battery, and each will have different currents. Each will have different currents. And we all know the equations. Now VA, what is VA? VA is equal to E minus IAR. VB is equal to E minus IBR. VC is equal to E minus ICR. Can someone tell me which voltmeter has the highest internal resistance? They have given you the values, right? VA, VB, VC. Let's do some analysis. Now we can say VA is bigger than VB than VC. That means in VA we have subtracted a small number, right? In VA we have subtracted a small number. So I can say IAR, it's smaller, IBR, ICR. Hope you can understand this. Because if VB is a larger value, that means the value we have subtracted is a smaller one. If Vc is small, that means we have subtracted a large number because E is constant for everything. E is constant for everything. E is probably 9 volt. E is probably 9 volt. We don't know. It could be 10 volt also. We don't know. Right. That means IA, IB, IC. Tell me then about the internal resistances of the voltmeter. These things you don't have to do, but in future if they ask you to do some comparisons, this is how it's going to be. Internal resistance should be the other way around, because E and R are same, E and R same, E and R same. So wherever we have a larger internal resistance for the voltmeter, current will be less. Okay, but what they are doing now is they are putting every voltmeter in parallel now. They are putting every voltmeter in parallel to the battery. VA, VB, VC. Now what will happen when you put all the voltmeters in parallel, people? Tell me. What will happen? When you put all the voltmeters in parallel, what will happen? This is E, this is R. Now there's going to be a current coming out here of the battery. Let's say the current is I and the voltmeter reading is V now, V. And all of them will have V across them because they are connected in parallel. That's why look at all the answers. In all the answers, the values are equal. You will never be able to calculate these values, but you will be able to guess the values. Guess the values. How is that? Now this circuit, people, it is equivalent to, you can convert this to a single circuit. How? This R. No? All of them have internal resistance. No? RA, RB, RC. They all will have internal resistances. So you can consider all of them together as R. Here E, here simple R, and the voltage across this one is V, and voltage across this R is also V, and the current coming out is I. Can someone tell me a relationship between R, RA, RB, RC? Tell me. What about R, RA, RB, RC? R will be less than all of them, all three of them. Do you agree with me or not? R will be less than all three of them. Why? Because R is the resultant. R is the resultant of RA, RB, RC in parallel. Then what can you say about this current I, people? So what can I say about current I? So I will be less than all these, no, I will be greater than all these individual currents. So I have a I here and I have IA, IB, IC. So I can say I will be bigger than all these currents. Can you agree with me on that? Why? Individual, now here IA is because of no, IA is because of RA, IB is because of RB, IC is because of RC, and this I is because of R. R is the resultant of all three resistors. When you put all three resistors in parallel, you will get a resultant resistor which is smaller than all of them individual, all the individual resistors. So we should get the largest current in this. The largest current will be coming out because when you put resistors in parallel, the resultant will be smaller than everything. So if the current coming out is largest, the potential difference will be the smallest. Okay, so V equals E minus IR. So we should say V should be smaller than all VA, VB and VC. And which answer is suitable for that, people? Which answer is suitable for that? Fourth one. Fourth one is a suitable answer. Why is fifth one wrong? Tell me, why is fifth one wrong? Can someone tell me why fifth one is wrong? Because in fifth one also we have answers less than fifth one is wrong because readings can't be different. No? Different readings, yes. Voltmeter readings can't be different. Readings cannot be different because voltmeters are in parallel. That's why the last one is wrong, and the first answers are not possible because when you put the resistors in parallel, the resultant resistance will be smaller than all the individual resistors. Therefore, you should get a large current. When the current is large, the potential difference is what? Potential difference is small. So this is wrong. Fifth one can't be the answer, but fourth one okay. Fourth one is possible because it is less than all these numbers: 8.95, 8.85, 8.75. Okay, fourth one, right. They are asking for the voltmeter readings of each in this situation, and all of them are connected in parallel. Therefore, they will have the same reading. Okay, first three questions are not very convenient ones. They are little complicated, but can't help. That is how it is, no? To allow only 20% of the total current to flow through an ammeter of resistance 96 ohm, the shunt required. Now, this is a shunt resistor type question. I think this will be a good one. Shunt resistor type question. So, how do you apply? How do you approach this question? Read it again. To allow only 20% of total current, to allow only 20% of the total current to flow through an ammeter of resistance 96 ohm, what is the shunt required? Right. So now, interesting. They have not given any numbers, but they have given us a percentage. Let's say there is a current coming. That current will take it as I. And now that current you are allowing it to flow through an ammeter, and there will be a shunt connected in parallel. Let's take it as RS. To allow only 20% of the total current to flow through an ammeter. So tell me, what's the current through the ammeter, people? Current through the ammeter must be 20 over 100 I. Yeah, 20 over 100 I, which is equal to 0.2 I. That means the remaining current should flow through here. That is 0.8 I. So 0.8 I current will flow through this. I think they have provided us the internal resistance of the ammeter, 96 ohm, no? 96 ohm, and we have to find out RS. We have to find out the value of RS. And we all know whatever the voltage we have across this, we will have across this. So I will take it as Vs and Va. Okay, Vs and Va. Vs is the voltage across the shunt. Va is the voltage across the ammeter. Let's finish this off. We know Va should be equal to Vs. Why? Because A and Rs are parallel. When you put two components in parallel, the voltage across them will be equal. So what is the voltage across A? That is IARA. What is the voltage across the shunt? ISRS. So IA is 0.2 I, RA is 96, IS, the current through the shunt, is 0.8 I into RS. Fine, if you simplify this, you will be getting 4 here and a 1 here. Therefore, RS is going to be equal to 96 over 4. I'm getting 24 ohm. Anyone else who got 24 ohm? 24 ohm. Okay. Right. So while I explain, you also can try this question. Not that difficult, no? This is exactly what we did just a little while ago. So instead of giving exact numbers, they have given the percentage. So it's all about just considering the percentage. That's it. Right. Let's move on to the next one now. Right. Next question. We have an ammeter and voltmeter. Interesting. Now this is going to give you a good perspective about voltmeters and ammeters. Let's see what it is. In the circuit shown, the ammeter A has negligible internal resistance. Ammeter A has negligible internal resistance. That means its resistance is internal resistance is what? 0. No? It will have an internal resistance of 0. It will mark that carefully here. Internal resistance of the ammeter, I'll take it as RA, that is equal to 0. When the voltmeter is removed from the circuit, ammeter reading will change by 1.5 milliampere. The internal resistance of the voltmeter. Nice. Right, so voltmeter has an internal resistance. We'll take it as RV. It has an internal resistance. We don't know what that is. Now we have to, in situations like this, we have to consider two circuits. We have to draw two circuits. First, we'll consider a circuit without voltmeter. So I'll draw a circuit without voltmeter. When you draw a circuit without voltmeter, what is going to happen? Ammeter is here. Ammeter has no resistance, so we don't have to worry about it. We have 1000 ohm. This is 2000 ohm, and this is 9 volt. There is no internal resistance to the battery as well. There will be a current I1, and the ammeter reading is I1. Correct? Ammeter reading is I1. What is the value of I1? You can easily find it. Sigma E equals sigma IR. Sigma E is 9. Sigma IR is going to be I1 into 1000 plus 2000. So I1 is equal to 9 over 3000, that is 3 over 1000, and I'm getting 3 milliampere. I'm using milliampere because I mean it's 3 into 10 to the power minus 3 ampere, which is 3 milliampere, because they have given answers in milliampere here. 3 milliampere. Okay, people. Now this is without voltmeter. This is without the voltmeter. Now let's consider what happens with the voltmeter. With voltmeter. Now with voltmeter, what are they saying? When the voltmeter is removed from the circuit, ammeter reading will change by 1.5 milliampere. Now let's put the ammeter. When I put the ammeter, what is going to happen? Will the, not ammeter, rather voltmeter, will the reading of the ammeter increase or decrease, people? Tell me. You have to answer it carefully. We have the ammeter. Ammeter doesn't have any resistance, no problem there. And here we have 1000 ohm, and we have 2000 ohm, and then we have the voltmeter here. Yeah, what will happen? No, I'm putting it back. When I put the voltmeter now, this is 2000 ohm, this is 1000 ohm, right? When you put the voltmeter has an internal resistance RV. The resultant of these two together will be less than what? 2000. Will be less than 2000. Will be less than 2000. The resultant of these two resistors will be less than 2000. Earlier it was 2000 and 2000. When I put another resistor in parallel, the resultant of these two will be smaller than 2000. So ammeter reading will increase. Ammeter reading will increase. Okay, ammeter reading will increase. Therefore, this is I2. I2 will be now 3 plus 1.5, that is 4.5 milliampere. 4.5 milliampere. Wait, I will explain that again. Now this circuit can be considered like this, no, people. This circuit can be considered like this. A single, we'll shrink it. How do you shrink it? We'll leave ammeter like this, and we'll leave the 1000 ohm like that, and then instead of these two, we'll take it as R. This is 1000 ohm, and here R. Okay, R. What is R? R resultant of 2000 ohm and RV in parallel. And what can I say about R, people? So R, so definitely R should be what? Less than 2000. Hope you can understand. Hikmahatim, do you understood? I don't know whether you had sent an answer saying decreasing. Don't know whether that's for the resistance or current. Now, when you put two resistors in parallel, people, the resultant resistance is less than both of them, individual resistors, no, 2000. So you can definitely say I2 will be greater than I1, because I1 is for 9 volt battery and 1000 and 2000 in series. I2 is for 9 volt battery. I2 is for 9 volt battery and 1000 and R in series, and we know R is definitely what? Less than 2000. So I2 is going to be a larger current, bigger current, and the change is given as 1.5 milliampere. Change means it could be less or more, but here we have figured out I2 is more, 4.5 milliampere. I2 is going to be equal to 4.5 milliampere. That's it. I think we can now finish it off. 4.5 milliampere. But before that, let me do something like this. Now R, what is the value, what is the equation for R then? R is going to be the here. R is the resultant of 2000 ohm and RV in parallel, na people. Therefore, I can write an equation for R directly. How is that? R equal to multiplication of the resistors divided by the addition of the resistors. Okay, right. So what I can do here is what can I do? I have to find the voltage across this one, no people. Yeah, I have to find the voltage across this one. How do I find the voltage across this one? Not current, I2 is known. Yeah, find the voltage across this one. Yeah, we'll do it this way. Now see, we'll take the voltage across this one as V1, the voltage across this one as V2. All right, so V1 we can find it how? 1000 ohm. If you put V equal IR, what is V1? V1 is equal to, current is 4.5 milliampere, so 4.5 into 10 to the power minus 3 into resistance is 1000. Therefore V1 is equal to 4.5 volt. If V1 is 4.5 volt, what is V2? What is V2? V2 is going to be equal to 9 minus 4.5. Total voltage is 9. From that, when you subtract 4.5, V2 is also 4.5 volt. Then for that particular R, you can apply V equal IR. Sorry people, there was a short power cut. Is it? There was a short power cut, sorry, but I took a screenshot of that quickly. Where is it? Yeah. Good. Sorted. Where is that? Right, this is where we were. Okay, so we have found out the voltage across. We have found out the voltage across who? We have found out the voltage across this one. This one V1 we can find, because we know the resistor of that, we know the current through that, so I can find the voltage across that one. If the voltage across that one is 4.5, total is 9, the voltage across this one is also 4.5, and for this one I'm going to apply V equal IR. Voltage is 4.5 and the current going through that is also 4.5 milliampere. Then I can find the value for R. So R is going to be equal to 4.5 divided by 4.5 into 10 to the power minus 3, and that is how much? Minus 3, sorry, 1000 ohm. That is R. And R, people, remember, R is the resultant of this. R is the resultant of 2000 and RV. That's it, done. And then we know, but we have just figured out R is equal to 2000 RV over 2000 plus RV. For R you can put 2000 now. 2000, that is equal, sorry, 1000, not 2000, equal to 2000 RV over 2000 plus RV. Hence you can cancel out these 3 zeros gone. I think RV will be 2000 ohm, is it? Yeah, RV will, if you simplify this, you will be getting 2000 ohm for RV. You don't have to do all these things, but I'm just show the step. Now if this is 4.5 and this is 4.5, these should be equal in magnitude, no, the resistors. If the voltage is separated equally 4.5, 4.5, if this is 1000, R also has to be 1000. R is 2000 and something else put in parallel, so both have to be 2000, then only you will get 1000 here also. Like that also you can do without all these calculations, but anyways I have shown every step in calculation, hence the answer for this question is fourth one. Answer for this question is fourth one. Okay, so whenever they say something is removed, something is added, go for a diagram without that component and go for a diagram with the component, then compare both. So a lot of things to analyze here, resultant resistance, how does a voltmeter work. It's more not really about voltmeter, no people, it's not really about voltmeter here, it's about not Kirchhoff's law, I mean taking resultant resistance, shrinking the circuits, and potential divider method. That's what's happening here really. The answer for this is fourth one. If you couldn't do this, try that again. Fine. Now let's move on to the next part. Next question. Sixth one. Right. What is this? Interesting. Okay. Consider the following statements made about the potential difference across XY of the circuits P and Q shown in the figures. Both cells have EMF E and negligible internal resistance. Good. Negligible internal resistance. Right. What's going to happen now? People, this is a battery E, and they have put two capacitors in series, and they have put two resistors in series. Both are equal in magnitude. See, 100 ohm, 100 ohm, 10 microfarad, 10 microfarad. So what will happen, tell you? This E will be equally distributed among these two, E by 2, and here also E by 2. I hope it is clear. E by 2. Here also the same thing is going to happen. Since they are using equal magnitude of resistors, the voltage will be equally distributed, E by 2, E by 2. The potential differences across XY in both circuits are equal. That is correct, because it is E by 2. Equally will be distributed. There is no internal resistance. That is also an important point. If a voltmeter with finite internal resistance is connected across XY, it will read a steady non-zero voltage only in Q. Steady non-zero voltage only in Q. What is it? If a voltmeter with finite internal resistance is connected across XY, okay, it will read a steady non-zero voltage only in Q. So what will happen here? What will happen here if I put a voltmeter with finite internal resistance? It will show E by 2 here, and here steady finite. Right, okay. If the voltmeter is ideal, both the circuits will provide the same voltage reading across XY. Yeah, that's correct. That's correct. Because we can show it. Because what is it for ideal voltmeter? For ideal voltmeter, internal resistance is infinity. Internal resistance is infinity. Internal resistance is infinity. So no current flows through it. Okay. When you put an ideal voltmeter, it's like it will always force through it, and it will always show the accurate reading, It will not alter the reading, original voltage, no? And it will not alter the original voltage. That's something we need to know. So definitely A and C are correct, people. If A and C are correct, these answers are not possible. First is not possible, second is not possible, third is not possible. So it's between fourth and fifth. We have to decide B. B is also correct. I'll tell you why. B is also correct. I'll tell you why. Now, listen now. What will happen when you put a voltmeter here? If I put a voltmeter here, now this is the circuit. Now if you put a voltmeter with finite resistance, what do you think will happen here? You're putting a voltmeter across a capacitor, people. What will happen? Like this, CC. And here also you are putting, a voltmeter across a resistor, across a resistor. So I'm talking about a non-ideal voltmeter. This is a non-ideal voltmeter. Finite internal resistance. This is also finite internal resistance. When you have a resistor like this, when you have two resistors like this voltmeter is going to show you a constant reading. There will be no change. It will not be E by 2 exactly now, because this voltmeter will also have a resistance to people. So we have to take the resultant of these two, right? Fine. We'll show a fixed reading. We'll show a fixed reading. No problem there. We'll show a fixed reading. But within bracket I'll put that, but not equal to E by 2. But not equal to E by 2. Why is that, people? Why will it not be equal to E by 2? Because this voltmeter also has a resistor now. So when I shrink them, this is R, this is not R, it will be less than R, a different value. This will not show a steady reading. This will not show a steady reading. Can someone tell me why? Once the voltmeter is connected to capacitor, what will happen? Once the voltmeter is connected to capacitor, what will happen? Once the voltmeter is connected to capacitor, connected across capacitor, current will start flowing. Capacitor will get discharged. Capacitor will get discharged. Capacitor will get discharged. It will start giving out the charges it had saved all this time, people. Capacitor will get discharged. Yeah, and when capacitor gets discharged, we have learned, so current will keep reducing. Current will keep reducing. If current keeps reducing, what will happen to the voltmeter reading? Current will keep reducing, so voltmeter reading is not steady. Understand? That is how you have to argue statement B. Both the systems are steady. Suddenly you are putting a voltmeter with finite resistance. This will not happen if you put an infinite resistance. If you put an ideal voltmeter, because it has infinitely large resistance, it will not allow current to flow through it. So capacitor doesn't have to give out its charge. But if you put a voltmeter with finite resistance, capacitor will start getting discharged. Therefore, the charge across the capacitor will keep changing. We know voltage across the capacitor is given by Q. What is it? Q equals CV. Q equals CV. So when Q changes, V will change. If V changes, the voltmeter reading will keep changing. Okay, this is also correct. Why? Because capacitor gets discharged. Capacitor gets discharged. Capacitor gets discharged in P, and charge across that will reduce. Charge across that will reduce. We have learned Q equals CV. So when the charge across that reduces, what should happen to voltage? Well, it will also reduce. So it will not be steady. So not steady, but it will not happen if the voltmeter is ideal, because if the voltmeter is ideal, it will not allow the current to flow through it. If you use an ideal voltmeter, put that also. If you put an ideal voltmeter, people, nothing will happen, no change. It is ideal. Ideal voltmeter. That way I have written ideal. So when current becomes 0, will it read E by 2 for the first case? Oh, wait. When current becomes 0, what will happen? No. It won't read E by 2. It won't read E by 2. It won't read E by 2. It will change because now it's getting discharged. No? It will not be steady. It will not be steady. When current becomes 0, will it read E by 2? Yeah. It will come back to E by 2, right? Because when this will become steady once again, can it become E by 2? Because there won't, once it reaches steady state, current can't change. But it won't be E by 2. Can it be E by 2 after that? No. Because this will lose charge, and will this release charge to it until, I don't know. It's a bit complicated. Now, when you put a voltmeter here, suddenly you are creating a path where the charges can flow. We'll get back to that. Okay, we'll talk about that later. Now, when you have an ideal voltmeter here, ideal does not allow current. Current doesn't flow. Does not flow. So no change. So no change in charge stored in capacitor. Q equals EV. So V is also, this is constant. Both are constants. If V is Q is constant, V is also constant. Will not change. If you put ideal voltmeter, fine. Okay. So what's the correct answer? Answer should be fifth one for this. Answer should be fifth one. So most of these questions, see, this is why I told you they are not just calculations. You need to get an idea about how to handle these questions. Good. Okay. Right. Then you have 7. Okay. So time is up, I guess. 9 o'clock already. We'll stop here, and we'll continue the rest at the next class. So you guys can now go through the next questions. Now 7, 8, 9, 10. There are not many, na? There are around 10 more. 10 from 6. We have done 6, no? There are around 10 more until 2016. Go through 17, 18, 19. There'll be around 10 to 15 questions. Please try them on your own, right? After that, let's discuss the remaining. We have to do all these questions somehow in electricity. How many are there? 59, 90, 116, 126, 141, 166 MCQs. You have to do all of them, because electricity and all, knowing the theory is not good enough at all. You need to know how to apply it. Now every question is different, people, they approach you, not different in the sense, for different questions, Kirchhoff's law was different. For this question, the way we applied was different. You have to have a good basic understanding about electricity. For that, you have to try as many questions as possible.